Professor Senatore is here.
Yes. Yeah. Hi, everybody.
You can share the screen.
Yes, I will.
And start your presentation. The title of the work of Professor Senatore is Extended Integrated Force Method for the Analysis of Prestress-stable, Statistical and
Statically determinate and
indeterminate structures.
Yeah. Okay.
Thank you so much.
Yeah, sure. So this is a new force method. We believe it's the first force method fully automated that can predict the response of kinematically indeterminate systems, which are those systems that contain mechanisms, and largely speaking, cable net, tensegrity, or systems like the one shown in the picture. Existing force method, they are not fully automated. And in comparison to the better known stiffness method, which can deal with such systems, the method that we propose offers a deeper insight into the response of the structures because it decouples the extensional from the inextensional part due to the mechanism modes. An important assumption is that the mechanism are first order infinitesimal. So that means that when the mechanism is displaced, there is no first order deformation of the element, hence we call them inextensional. But second order changes might indeed occur. Briefly, the existing integrated force method, which is based on equilibrium equation and compatibility through the self-stress states, which can be obtained by singular value decomposition of the equilibrium matrix. And there is also this quantity we need to keep our attention on, which is the mechanism mode, which is the left null space. What happens with these equations when the load lies in this space, there is no solution to the equilibrium equation. Simply because I think this example is effective if the load is oriented in this direction, the vertical, and there is no pre-stress in these two members, then the classic equilibrium equation, they just break. So the total displacement cannot be uniquely determined solely through the element forces. And this happens when the load lies in the left null space of the equilibrium agent, which is that UM. So what we did is to introduce the concept of product force, which was first introduced by Pellegrino and Calladine, is to use this concept. So the product force is basically the unbalanced force that arises as the mechanism is displaced due to the element pre-stress. So as the element reorienting space, because they are pre-stressed, even if there is a components of load that excite the mechanisms, due to the pre-stress and the reorientation of the elements, there is an unbalanced force that can actually equilibrate the mechanism. So the product force can be used in a procedure that we propose, which aims at obtaining the appropriate pre-stress that can stabilize all the mechanism in the system. And this is done by making sure that this quantity, which is basically the product or the product force of the unbalanced forces times the mechanism modes, is always a positive definite entry. So this matrix is a positive definite matrix. And we solve this problem through semi-definite programming, which produces a global optimum through interior primal dual, through primal dual interior point algorithm. And the point to keep our attention on is that through this method, we obtain the pre-stress that guarantees that all mechanisms in the system have positive stiffness. That's the main concept is like through pre-stress, we can stabilize the mechanism. And once they're stabilized, then we can obtain a solution in terms of forces and displacement. Interestingly, we also include the so-called eigenstrain in the design variables. The eigenstrain can be thought of as the initial element deformation. So if you think of a structure that you need to change the length of the element such that a change of shape stabilizes the system. We use this concept of eigenstrain in active control, where instead of modeling the imperfection, we model the length of the change of length of actuators that are embedded in structures. So we use the same idea here. Once the product force is obtained, then it's relatively easy to extend the existing IFM equilibrium equation so that the primary unknown becomes the internal forces, that the coefficient of the mechanism modes, whereby we can obtain the extensional part of the displacement caused by the load and the mechanism. And the extensional part is simply obtained by using the orthogonality between the product force and the extensional displacement. This method is fully automated, so it is equivalent to the better known stiffness method. They're both polynomial third order, but our method, well, the IFME, gives a deeper insight because it also gives you the extensional part of the mechanism. Why you want to know that is because when you apply pre-stress, it can tell you how much stiffness you are imparting to the mechanism through the pre-stress. So it's an important quantity. Time is running out, but if I have one more minute, I'll show you 2 case studies. Good comparison with analytical solution. We overestimate the displacement, which is conservative, because we underestimate the stiffness of the mechanism due to the first order infinitesimal assumption. For more complex structures like this triplets and secretary towers, it's interesting to see that we obtain the extensional and the inextensional part, which is even more obvious in this case. We have like a simple cross-bracing system with 2 actuators. In this case, the pre-stress is directly imparted through length of change of the actuators. If a load the orthogonal applied in the orthogonal plane and the out of plane determine a displacement of 20 millimeter by applying a further change of length, then we can halve the inextensional displacement. So this shows you directly what effect has further pre-stress has on the stabilization on the mechanisms. And here we close with the leaving the conclusion open to questions if there is any.
Well, thank you so much, Professor Senatore, for the nice presentation. Are there any questions, please? Okay, Stefano, I have a question. Please, Stefano.
Yes, here.
Okay, sorry.
I was muted, sorry. Thank you, Gennaro. It's ever really interesting. So just a clarification about the matrix G. Is the matrix G dependent on the actual configuration? And how do you manage with this in the algorithm? And another question: did you try to compare some solution with some kind of approaches like Rick's approach or this kind of algorithm, path following approaches?
Sure. So the first question about what G is. So G, you can think of G as kind of the stiffness of the mechanism in a way. You see, so the delta A is the change of orientation of the elements, and then WS is the state of self-stress, and alpha is a coefficient. So these products, WS times A, is effectively the pre-stress. So so there exist M product forces if there are M mechanism in the structure. And the M mechanism of the structures are given by the mechanism modes that you obtain from singular value of the decomposition. So this is linear, so this is a linear method, yeah, so it's not non-linear, right?
Is a relative of the what we can call in other methods geometrical stiffness. It's
similar to the geometric stiffness. That would be the equivalent if you use the stiffness method, yes. So if you use the stiffness method, you build the geometric stiffness matrix. But if you use the force method, you use, or at least we use the concept of the product force. Okay, so they are related, but they're not identical. You can show that the product force is in fact is the projection on the mechanism space of the geometric stiffness matrix, but they're not identical. So the important part is that how to deal with it. Like, so if you ensure that this product is positive definite, then it means that you are applying a pre-stress that can stabilize all mechanism in the system. And so you build G, the matrix G, through as a result of the solution of this semi-definite programming problem. And once G is obtained, So this problem basically tells you also if the structure is pre-stress stable. So if there is a solution to this problem, because it is a global optimum, then it is a confirmation that the structure can be stabilized indeed through pre-stress, because not all kinematically indeterminate system can be stabilized. But if there is a solution, it means that the structure is pre-stress stable, so-called pre-stress stable. And so you can then continue with the augmented equilibrium and compatibility equation to obtain forces and displacement.
Okay, thank you.
The second question is that we do not compare with nonlinear methods because, well, we compare with nonlinear method for some example, and the answer, if I remember correctly, is pretty close. That we provide, this work is published in the International Journal of Solid Structures, so you can find that in there. It was like a less than 10% different to nonlinear method, but it is good to remember this is a linear method, yeah. So like it does not iterate through a configuration of equilibrium. It's a one-step procedure if you want to call it that way. Yeah.
Thank you, Gennaro.
Cool.
More clear now. Thank you.
Cool.
Thank you so much.